the specific task of object detection. Isaac ROS provides a package for object detection based on DetectNet. DetectNet is similar to other popular object detection models, such as YOLO v3, Faster RCNN, and SSD. Here are some of the models currently supported by Isaac ROS. You have car detection and tracking, you have people counting and face detection. All these models are from NVIDIA NGC, which is a portal of services and software for AI and machine learning solutions. NGC offers ready-to-use containers, pre-trained models, and SDKs for speedy deployment in various use cases. Now, if we are interested in deploying our own models with Isaac ROS object detection, how would we do that? Let's see. Coming to object detection with YOLO v5. YOLO stands for You Only Look Once, and this is a collection of models trained on the COCO dataset. COCO has 80 object categories of common objects that we see around us. For example, car, dog, laptop, or book. YOLO v5 has been implemented in PyTorch by Ultralytics, and it's a single-stage object detector. What that means is that the model directly predicts bounding boxes for detected objects in an image without any intermediate tasks. So this generally results in a simpler and a faster architecture. There is another type of object detectors called two-stage detectors, which use a proposal network first to find objects and a second network to filter proposals and to give a prediction. We're going to understand more about YOLO v5 very soon, but before that, it's important to know that YOLO v5 is available in multiple models with different parameter sizes and hence offering different accuracy and performance. The model that you pick would then depend on your type of application or device that you want to run detection on. Okay, so now that we have some background about NVIDIA Isaac ROS, object detection, and YOLO v5, it's time to understand how to actually bring your own models to NVIDIA Isaac ROS. The first step is preparing your model. We chose the small model or YOLO v5s because it gives a good balance of accuracy and speed, and it's not too large to run on edge devices like NVIDIA Jetson. The Isaac ROS TensorRT inference node takes in a model for performing inference and currently only supports ONNX and TensorRT engine files. Ultralytics provides an option to export their PyTorch model to a number of forms, including ONNX, so I just used that to convert the YOLO v5 PyTorch model to ONNX. For those of you who don't know, ONNX is a common file format to represent machine learning models and to use them with a variety of frameworks and compilers. If you've trained your model using the NVIDIA Tau toolkit, it can be used with Isaac ROS TNN inference by converting it to a TensorRT engine first via the Tau converter tool. Tau converter generates an optimized TensorRT engine file from the exported ETLT model file. It's very important to visualize your model and to know what the input and output layers look like, since that is how an inference pipeline will actually interact with your model. The Isaac ROS inference pipeline is structured as an encoder node and a decoder node with the model sandwiched in between for inference. We'll get into the details soon, but essentially the encoder needs to know what input names and dimensions the model expects, and the decoder needs to have that same information about the model's output. Netron is a pretty good tool to visualize your models. You just have to upload your ONNX model to Netron and it shows all the model layers in a graph form. So these are the input and output parts of the YOLO v5s model from Netron, and it shows that this network expects an input image size of 1 by 3 by 640 by 640 and an output size of 1 by 25,285. Here the first number 1 represents batch size, and the output size depends on the input dimensions, which we'll get to in a bit. So with that background, I'd like to explain the development setup and Isaac ROS requirements. All Isaac ROS packages are designed to be compatible with ROS2 Humble and run on Jetson or an x86-64 system with an NVIDIA GPU. To simplify development setup, it's strongly recommended to use the Isaac ROS dev Docker. This provides an environment with all the dependencies you need to run Isaac ROS gems. Steps to using it are linked here, and all Isaac ROS examples have been tested with this Docker image as a prerequisite. So once you follow those steps but are not inside the container yet, you have to create a ROS2 workspace named Workspaces and clone packages in the src folder. These are the commands to doing this. Clone the Isaac ROS common repo since it contains all the scripts and Docker files for the Isaac ROS suite. And if I want to use the Isaac ROS DNN inference package, for example, I would clone that here too. So eventually, your src folder would look something like this with all the repositories of interest. Then you launch the Docker container using these commands here. Once you're inside the container, you need to first build and source the workspace before you can actually run packages. So you would do that by following the commands here. Now, coming to the setup for object detection, I tested this project on a Jetson Orin running the latest Jetpack and the latest ROS2 release Humble. For live input, I used the Intel RealSense webcam, since this is an RGB plus depth camera, which can be useful in a robotic system for other tasks like depth perception. I used the Isaac ROS development container that we just talked about, which contains all required dependencies, and it was pretty quick to set up and to work with. So here is a sneak peek of object detection using our YOLO v5 pipeline. This is the project workflow for YOLO v5 object detection using Isaac ROS. Live input comes in from the RealSense camera and is communicated as a ROS2 image message type. Next, we have the Isaac ROS DNN encoder node that converts this image message into an Isaac ROS tensor list message. This tensor list is consumed by the TensorRT inference node along with the model that we provide. The Triton inference node could be used here too in place of the TensorRT node, and we'll see that pipeline in the next slide. Now, the output of this node is also a tensor list message and is passed to the decoder node. For vision models, we can use the encoder and the TensorRT or the Triton inference nodes as is, but the decoder node has to be written based on the particular model's output. The decoder has to do two things. First, it has to parse inference results in the right format from this tensor list message. And second, it has to create an appropriate ROS message type for communicating results. For instance, detection 2D array is the right message type for object detection. Finally, we have a simple visualization node to view bounding boxes on the input image. And you can use RQT or other tools like Foxglove to visualize these results. Here is the project workflow using Triton for inference instead of TensorRT. The advantages of using Triton is more flexibility since it supports more backends like Onyx Runtime, TensorRT, PyTorch, and TensorFlow. If you want to use it with a TensorRT plan file, you can use tools like Tau Converter or TRT-exec to convert your Onyx model to a TensorRT plan. The camera input node, encoder node, and the decoder node work the same in this pipeline. The only thing that changes is that the Triton inference node takes a config file along with the model plan file as input. Since it takes a tensor list from the encoder node and also outputs a tensor list to the decoder node, no other changes need to be made to the pipeline. Now, let's get into more detail about each node in the pipeline one at a time, starting with the Isaac ROS DNN encoder node. This node takes images from the camera node, link to the camera node is provided in the slide, and converts these images into tensors, which are used by the inference node. These encoded tensors contain information about the input, including the shape, the data type, and the actual image data. The encoder node takes some parameters like the input image dimensions expected by the network, for example 640 by 640 for image height and width. We also know how to get this dimension information from Netron when we talked about visualizing our model earlier. One thing to note here is that Isaac ROS currently only provides an image encoder which is appropriate for vision models like detection and segmentation that take images as input. This encoder cannot be used as is for a language model that expects strings as input, for example. Now let's deep dive into the next node in the pipeline, the Isaac ROS TensorRT node. This node takes in our model and the encoded image tensors from the encoder node and performs object detection. It can take the model either as a TensorRT engine file or an ONNX model directly, which it converts to a TensorRT engine file itself. The node takes some parameters like the input and output binding names to be used with the model. For example, images and output 0, which we found earlier using Netron. Finally, the inference results are output as a TensorList message. The Isaac-ROS Triton node performs the same function as the TensorRT node, but supports backends for more model formats like ONNX, PyTorch, TensorFlow, and TensorRT. In addition to the model, you have to provide a config file to the node which specifies what backend to use, for instance, TensorRT or ONNX runtime. This config file also specifies input and output data types, dimensions, etc. Again, inference results are output as a TensorList message, which is now our decoder's responsibility to extract detection information from. Here is the decoder node. Its job is to parse your model's output into a meaningful format. For YOLO v5s, tensors from the TensorRT or Triton inference node need to be parsed into information that can define object detections. For each object, this includes bounding box information, so that would be the bounding box center coordinates, the bounding box height and width, the object category or class, and the confidence score. This information can then be packed into a ROS2 detection 2D array message. So each detection 2D array message contains all the detections in an image, and each detection message within it holds the information we just talked about. The YOLO v5 decoder node takes some parameters like confidence threshold, IOU threshold, but the question still remains, to write the decoder, how do we know how to parse the model's output tensor to this bounding box information, object class, and confidence, etc.? Okay, this is a pretty interesting part. Now, to understand what a decoder has to do, you have to understand your model's output. We're going to spend some time understanding this for YOLO v5s. So in YOLO, as images pass through the network, three main detection layers break it down into grids of different sizes. These grids are actually feature maps, and they capture features in the image at different abstraction levels. Simply put, each feature map describes different characteristics of the image. Within a feature map, or we could also call it a grid, imagine each cell having anchors to check the confidence score and the class probabilities to identify if there is an object in that cell at all. For each cell, each anchor outputs a prediction. So we have three anchors here, let's say in the red, green, and blue, which contain information that we'll zoom into in the next slide. How are the anchor predictions actually packing information of interest? In our case, we are interested in the bounding box information for detected objects, along with the object category and the confidence score of the detection. So let's understand how YOLO outputs results. From Netron, we know that for an input image of size 640 by 640, the model outputs a tensor of shape 1 by 25,200 by 85. Here 1 is the batch size and 85 is the number of classes plus 5. We know that the COCO dataset the model was trained on has 80 object categories. So where is this plus 5 coming from? Each prediction consists of the bounding box top left x coordinate and y coordinate, bounding box width and height, the confidence score, and the object category. But instead of a single number, the object category is represented as a list of probabilities. Probability of the object belonging to category 1, this is the probability of it belonging to category 2, and so on, up to the total number of categories the model has been trained to detect. That explains how you get this last value of 85 in the output shape. It's your number of classes plus 5. It's important to note here that Cx and Cy are not the actual final coordinates of the bounding box, but the relative offsets corresponding to a particular anchor box. Now, coming to this big value in the output, 25,200. Let's consider one cell in the image like we discussed earlier. This cell has 3 anchors, and each anchor represents the prediction with 85 features. So each cell now effectively has 3 times 85 features. YOLO accounts for these features by modifying the channel size of the grid. So let's say we have 3 grids of dimensions 80 by 80, 40 by 40, and 20 by 20, corresponding to the 3 main detection layers in YOLO. Now PyTorch represents this output in B, C, H, W form, where B represents the batch size, so 1 in our case. C represents the channel size, so 3 times 85 from above. And H by W represents the grid dimensions. So if we're currently considering the grid size of 80 by 80, then that number is represented here. To make this easier to work with, we reconstruct the output in this way: batch size by grid size by number of anchors by number of classes plus 5. You can see that all values are just in a different format here between these two forms. Now, if we have 3 grid sizes corresponding to 3 different detection layers, each grid would give us an output like this. So all these outputs need to be appended, giving us a final output that looks like this. Batch size stays the same at 1. The appended output from the 3 layers, assuming 80 by 80, 40 by 40, and 20 by 20 for grid dimensions, the number of anchors, or 3, and the number of classes, plus 5, or 85 in our case. Now, it's a little complex, but it might be more clear why this output dimension depends on the input image size, because grid sizes are determined by image size. Further calculations need to be done to retrieve the final output bounding box coordinates. But this is a link to an article that explains YOLO v3 in a good detailed way, and I found it pretty helpful for understanding more about anchor boxes and their output. Phew, understanding the model output was a little complex, but very important. Luckily, when it comes to implementation, you can find and use existing methods for popular models to speed up the development process. I used some post-processing methods from Ultralytics, most importantly, non-maximum suppression, or NMS. NMS filters through the multiple proposed bounding boxes for a given object and returns the final best fit box. Knowing how a model works and how it outputs inference goes a long way while debugging and using it in your applications. A note here is to check whether the model outputs information in the format your application is expecting. For example, if the model outputs bounding box information as top left and bottom right corner coordinates, but your application expects the top left corner coordinates, width, and height, then there is a mismatch there, which needs to be converted to the expected format. These are pretty straightforward changes, but necessary for your decoder to work correctly. Okay, we're coming towards the end of our detection pipeline. Visualization is important to debug and visually test your results, and it's also what's fun about working with vision models. The visualization node takes images from the camera node and detection messages from the YOLO v5 decoder node and creates a new image with the bounding boxes drawn around objects. It does this by matching the timestamps on the image and the detection message, so it's important that timestamps are communicated correctly throughout your pipeline. You can visualize the results on RQT or other tools like Foxglove. Foxglove Studio is a good open source tool to debug and visualize your ROS applications. I use their web version, but there's also an app which you can download. You can make a live connection to your system or can upload recorded data like a ROS bag and then visualize images, point clouds, and more. These are the different ways you can open your data based on whether you have a pre-recorded file like a ROS bag or if you want to connect to a live system. I chose to open a live connection, and these are some ways you can do that. There's a ROS bridge package for ROS1 and ROS2. There's Foxglove WebSocket. There's ROS1, ROS2, and Velodyne LiDAR connections. These last 3 are supported in the desktop app. I chose the first one, the ROS bridge package, because it can run in a browser and was pretty easy to set up. This option lets you connect to a running ROS1 or ROS2 system over WebSockets and needs a single port open between Studio and your robot. Steps are given on the Foxglove website, but essentially you just have to run a server node from the ROS Bridge Suite package, note the port it's listening on, and just enter it here. And voila, your system is connected, and you can now view ROS messages like in this window here. There's some information about the data source, the topics coming from your system, and you can add multiple panels here to the interface to visualize multiple topics at the same time. Here is a video of our object detection with the YOLO v5 decoder node and Isaac-ROS inference pipeline. You can see object labels and confidence scores along with the bounding boxes. These are some miscellaneous tips that I wanted to share during pipeline development. A ROS application often has multiple nodes working together to perform a task. Take our detection pipeline, for example. There are about 5 nodes: the camera node, the encoder node, the inference node, decoder, and the visualization node. So instead of opening a different terminal to run each node, you can create a single launch file for your entire pipeline that will load all of your nodes, which can then be run with a single command in a single terminal. This just makes things neater and more efficient, and most Isaac-ROS projects contain a launch file like this. So feel free to check it out on the NVIDIA Isaac-ROS GitHub. Second, remapping topic names. If your ROS node subscribes or publishes to a node developed by someone else, it's possible that there may be a mismatch in topic names. For example, the TensorRT inference node publishes results on a topic named tensor sub. But if your decoder node subscribes to a topic named results, it won't be able to get data from the inference node. So it's important to know what topic names each node communicates on and to remap topic names in case there is a mismatch. Remapping essentially means changing, and these remapping rules can easily be added to your pipeline's launch file. Third, while running on Jetson or NVIDIA GPUs, check that you're using the PyTorch built by NVIDIA with CUDA acceleration. If you want to upgrade, still make sure that it's the NVIDIA provided version. If you're using the Isaac-ROS dev container, you don't really have to worry about this since it comes with the CUDA accelerated PyTorch already installed. Okay, it's time for a quick recap on how to bring your own models to NVIDIA Isaac-ROS. 1. Set up your Isaac-ROS development environment. It's strongly recommended to work inside the Isaac-ROS dev container. 2. Convert your model to Onyx, visualize using Netron, and note input and output names and dimensions. Understand how the model outputs inference results. This is all very important in debugging and writing a decoder for your model. 3. Build the Isaac-ROS DNN inference project in your workspace. This includes the encoder and the inference nodes, and specify parameters based on your model. 4. Either implement decoder logic yourself or find an existing implementation. Write this as a ROS package that subscribes to an Isaac-ROS TensorList message and publishes a message of an appropriate type. For instance, a detection 2D array message for object detection results. 5. Test your results visually using tools like RQT or Foxglove.
Finally, we have on Isaac-ROS VisualSlam. We know how it works the algorithm, how it works the packages, how many parameters you can use. I only show a part of this parameter, which type of topic you need in input and output, and which type of parameters and services you can use it. Now let's jump on the demo. Okay, I was speaking before about Docker. This is something that you can use right now to work with Isaac-ROS VisualSlam. If you know about Docker, there is a Docker file. In a Docker file, you set up the environment, all software needed, all information you need to work with a specific software. It's like a bash with a list of install files. Really simple to explain, but more or less this is the view. To work with Isaac-ROS VisualSlam, you need to use the Isaac-ROS common. After that, you need to run a script that builds an image. And well, if you worked before with Isaac-ROS, I remember the nightmare to build every time the image. But the engineers made really a great job. Now you need only to run the script, and this script directly pull an image with all inside. You can directly work on Isaac-ROS. there are, and when you're inside the container, you're already working in an environment made for Isaac ROS with ROS2, with the GPU acceleration, designed for all Isaac ROS packages. After that, you can download in your workspace these packages: Isaac ROS Visual Slam, Isaac ROS Common, what is already downloaded, and Isaac ROS Nitros. With these three packages, you're able to run the builder and the ROS2 builder. After that, this is a demo if you want to use on Isaac Sim. In this case, you can use it for to test the localization, but you can use a RealSense. You can use which type of simulator you want, because finally in the end, we want an input for the Visual Slam and we want to read the topics. In this case, we need to open on Isaac Sim Carter, set up the environment, enable the condition for the stereo streaming, and finally play Isaac Sim to see the environment running. After that, we need to jump on Docker. I know, guys, Docker is simple, but we are already inside Docker if you follow this demo. After that, you run on a terminal Isaac ROS Visual Slam Sim, and in another terminal you can run the same script you've seen 2 pages before, and open another terminal with RViz to show the output. And if something's going wrong, remember, build, remove, build, install, Colcon build, or if it's not an issue or something about ROS, it's something about Isaac ROS Visual Slam, remember, we have our forum, and you can write or open an issue on GitHub. And this is what is happening working with Isaac ROS Visual Slam. In this case, I was running this feature, and meanwhile the robot is moving, I'm enable and disable the light. This is something that may be happening if you have low lights or high light. And look this video. There are moments when there are really no features. There is only a wall, and the localization always working. The robot is always localized, and the robot know where the robot is. And this is something that finally you want to use for your application. Okay, I'm really, I hope I'm not bothering you. And now let's see another point for the mapping. And this is another important action you can use for on Isaac ROS Visual Slam. Remember to run this command to store and save the map, and another command to load the map and localize. It's something really simple. You can run this feature on a terminal, or you can make another ROS2 node that when see example, just share an idea. When recognize an April tag, it's time to load a map or store a map. This can make autonomous the navigation. You can combine example to nav2 and make some different events together to store a map, load a map in real time for your robot. Okay, we are in the end of this presentation. Just recap. First step, where you can find it? You can find directly on Isaac ROS Visual Slam. Remember to start and clone this repository. You can use directly this QR code or copy and paste the link. Second step, remind, Isaac ROS Visual Slam work with NVIDIA Brush like an engine, and this engine manage all these features for you. We need only to enable, disable the feature you need it. voice work, the ROS2 package, there are different topic subscriber publishers, params. I'm really sorry, but I was sick in these days. Actions and services. Benchmarks, this is important. Voice work and the achievement and the capabilities of this package are really, really high, and you can use from today on your robot. If you never seen, or maybe you have issues, I made in the beginning of this year a webinar was based on how to set up an environment and work with a visual odometry, was the old name, without slam in the beginning of this year. And just to remind, we are really taking care of all our packages on Isaac ROS. In this case, it was a presentation about how to use, to tune, and was made on Foxy. Just to have an idea, if you maybe need a new update, please let me know.